Hello and welcome. We're starting an episode that is intended to be an overview of what is OpenVSwitch, how it works, how it is built, and why it is so important for us. As I told you before, I recommend you to get acquainted with OpenVSwitch internal workings, if only because it is a core switch for OpenStack, another open source product that is an extremely popular and free tool to build compute clouds. So OpenVSwitch is a virtual switch. It competes with all other virtual switches out in the market, and DV switch or Nexus 1K or Juniper vRouter all fit the same niche and is intended to be a middleman layer between the virtual machine interface card, the virtualized one, and the real host interface card that will be used to serialize traffic out. It serves as a network multiplexer by encapsulating VM traffic into separate VLANs, or in modern network, in separate overlay tunnels using protocols like VXLAN or NVGRE. Being a software, OpenVSwitch, like all other virtual switches out there, can report to some central entity and be configured from one central dashboard, thus already giving you some sort of an SDN solution, although without any visibility into a core physical network with real switches in between the hosts. OpenVSwitch is open source and accepts contribution from anyone, be it a single developer or a company, and in that it is modular. That is an extremely powerful feature that makes OpenVSwitch highly extensible. So what features it does support by now? Well, there are many. OpenVSwitch offers us a way to perform a traditional VLAN-based switching with STP, but also offers us a host of other features that by many are considered to be essential for any production-grade network. For example, very extensive suite of monitoring protocols, NetFlow, SFlow, IPFix, bidirectional forwarding detection, and very finely grained Linux facilities for QoS, as well as load balancing and port groups of different kinds, and IPv6 support. It supports both old-school IPsec and GRE tunnels, and as well newfangled VXLAN and NVGRE. More importantly, OpenFlow is an integral feature of OpenVSwitch. It is used for communication between OpenVSwitch components, and that is what makes OpenVSwitch a perfect candidate for any SDN lab. It is virtual, it is pure software so that it can be run in VM inside of a Linux OS. And also it has to support OpenFlow up to the newest 1.4. Architecturally, OpenVSwitch consists of a number of different applications that all work in concert to achieve a common goal. There are both user space and kernel space data path modules, and that is how all cool kids in a blog call switching core or data plane. And naturally, in all realistical setups, that will be a kernel module. This data path is a pure switching code. It is extremely fast and very simple. This data path, on every new stream or frame that is coming to the interface, consults with a vSwitch user space application that is more or less a control plane for this switch. that contains all the network state, port state, and essentially the flow table. Be it a traditional behavior with every switch a separate device, or an OpenFlow controlled SDN cloud, vSwitch-D is an interface that is used to talk to data path and configure data path rules, flow table. Finally, OpenFlow is used by other applications that interwork with OpenVSwitch to configure vSwitch-D and to set new rules into flow table. OVSDB, OpenVSwitch Database, is an application that carries everything OVS related in one single database with information about this switch, its configuration, its state, and all that. For every switch in the database, and in NUS there can be multiple, there will be a separate vSwitch-D process running and data path module depending on the interface it got new packet coming in will be consulting with that particular vSwitch-D instance. Then finally, there are a number of tools to manage all this framework. OVS dash commands are user space CLI utilities to configure that or this aspect of OpenVSwitch. Let's better see them all in action. First and foremost, if you want to use the newest OpenVSwitch, it is highly recommended to use an Ubuntu Linux of the latest stable release, as OpenVSwitch is highly dependent on new kernel features that appeared only in kernel 3.2 and later. Then, if you check your VM or real machine for a vSwitch package, you'll actually find a lot of packages that all are components to OpenVSwitch. Some of them are mandatory, like OpenVSwitch Switch or OpenVSwitch Common, and some of them are optional, like OpenVSwitch IPsec or Debug or a Neutron plugin. Neutron plugin, by the way, is the plugin that is used by OpenStack. So what do you do to explore OpenVSwitch? If you have all proper packages installed, you'll have a bunch of OVS commands, as we've seen on the graphic before. And OVS vsctl command is the one that is used to set up, destroy, and manage OVSDB entries, and with that to spawn new vSwitches and create configuration for them. The show command is the one you want to start with. Here you can see that it requires a root permission to run. Here we can already see that there is an entry to OVS database. And by the way, this first line is OVSDB key. And inside of the OVSDB, we can find one switch created with one configuration, basically, with a controller entry set up, some ports defined, and the OVS version provided for our convenience. So with show, we can explore what our entries are in the OVSDB database, and OVS OFCTL is the command to use for everything OpenFlow related. We can start with show as well, but this time it will require a switch name. Same mistake again. And unlike vsctl, this time we see port status report from the data plane over OpenFlow to control plane. And in port status report, we can see well, if port is up or down, and some other minutiae. And there is also OVS fctl dump flows command that can be used to actually look into the flow table. Surprise or not, but apparently the flow table of switch 1 is empty. It is a correct response. There is just no entries in there. Remember, if for an OpenFlow switch, flow table contains no appropriate match for a given flow, there will be a packet in message coming to the controller to do some calculation and make a decision and respond with a rule to be installed in this flow table and to apply on this flow. Well, we have a controller in works here, and we also have a way to try it in work. We can simulate a flow coming, and as you see, well, pings are working fine, the network connectivity is there. But if we'll try to do the same command again, now we can see some flows already created and installed into flow table. Flows can also have timeouts, the hard timeout for the flow to be removed after a number of seconds, or the soft timeout or idle timeout to make this rule disappear after a number of seconds without any flow matching to this particular rule. So let's take any of those two and examine them in detail. First, we can see that for every rule there is a statistics, how long this rule is here, idle age, and the table number this rule is installed in. This already hints us that we are not using OpenFlow 1.0. We have multiple tables, number of packets, and that is a counter, and then a byte counter for this rule. And finally, the rule itself, it is right here. There is a match structure that defines anything that comes to port number 1 with MAC address destination, C6, and so forth, and action to be performed. Output anything that matches this rule to port number 2. That is an example of a rule that can be seen in any OpenVis switch, although only if this switch uses OpenFlow for configuration. Let's check how it can be applied to a different OVS setup, this time a PK8 switch. So in PK8 switch, you can have two modes of operation. There is a way to manage the device with a special CLI, very much like iOS or JunoOS CLI, or there is a way to transform the switch into a regular Debian Linux machine with an OpenVis switch installed, and unlike the pure software switch, hardware accelerated, and manage it using your favorite OVS management tools like just a regular OpenVis switch. Here you can see a startup config shell script that I have created to, well, basically, let's try a different way, to basically set up a default VSCTL instance, reset it basically to delete and create it again, and we can see here how the data path type defines a driver to use, and that will be a hardware accelerated PK8 driver. And to set up a number of ports in trunk mode, and this switch is actually configured and set and resides in a data center, and is used to switch traffic between an OpenStack cloud hosts. There also is a command you can see here that currently isn't in use to set a remote controller for this switch. And this command actually makes or transforms the switch to a pure open flow switch, contrasted if it is absent by a hybrid open flow switch, the one that can work without the controller. OVS can behave both ways. So if you provide the controller IP or socket to connect to, you'll have your remote central control plane. If you don't, you just have a regular independent switch. Let's check if we can see this switch internals. On the PK8, we already have root admin rights, so we don't have to provide a sudo command. And yes, there is this configuration that you just have seen in the file already set in the OVS DB. And if we try to look into flow table of this switch, we can actually find a simple single rule. As we've seen in the file, the controller socket wasn't provided to the switch, and there is no controller configuration line in the OVS DB, as we've seen in the virtual environment before. But this line is basically a default behavior of OpenVSwitch. It says that anything with no match, priority 0 and no match structure, basically match everything, should be acted upon in a normal, independent way. No remote controller, just do your job. There's also a way to add new flows to this switch as well. Let's take, for example, this one, which is basically a description of broadcast and ARP flooding rules. Also, there are quite extensive rules regarding switching between two ports, but here you can find everywhere the same pattern. We define a priority, sometimes add a timeout or two, and the most important, we add a match clause, be it, say, match the VLAN or match the type of the frame or match the destination address or match IP address or anything else in the possibilities of OpenFlow, and the action list to perform. For example, I'll take this line. We match access VLAN, and then if it is ARP, we first flood it, then strip VLAN, and add this frame to the local interface, send it to the local interface of the switch. So basically, ARPs are flooded all over the trunks with VLAN tag. Then VLAN tag is stripped, and the final last copy of ARP, this time without VLAN tag, will be sent to the switch itself on its local interface. Every rule is built in the same way. The last command I wanted to show you regarding the OVS is so well hidden that I had to create an alias to it so that I do not forget how to use it. And it is OVS appctl with OFProto trace utility. Appctl in general is a command that is used for different utility functions, and OF Trace is a perfect tool to debug your Open vSwitch and the rules it has. For example, I will use my alias. If I'll try to send ARP in port 1, the switch will perform calculations inside and according to the flow table will do something, right? And the trace is the command that can be used to debug what conclusion the switch has come to. For bridge 0, for the flow with ARP and everything 0, 0, I did not provide any flow description, so no destination address, no ARP contents. We already know that it is ARP, so nothing inside of ARP. And action performed will be normal. And that is understandable. We have this single action right here. It is normal. So nothing like that. And then normal involves a decision by an independent switch, not by a controller. And we can see this decision here. That's what happens inside of a switch. That is probably more than enough for an introduction to OVS. Next time I'm going to show you how you can create your own virtual lab VM and experiment with all this software and virtual networks. See you next time, and thank you.